Welcome back to the series. So here we're going to be doing epsilon-delta proofs for the case where we're dealing with a function that is quadratic. So I have quite a lot of examples in here. So yes, it's going to be a lengthy video. You can stop at a point where you actually understand the concept, okay, of the epsilon delta, but I wanted to expose you to as many examples as I can and varieties, and then what to think about. I'm not going to go into the definition of the epsilon delta. I've done that already. So if you want to go back and kind of deja vu your definition, you can take a peek at that link, which is provided there for you. I also did a video for the first case, which is when our function within here is simply linear. And that one has a really nice process in terms of finding your delta for a given epsilon, and I'll put up a link up above there to the linear case. So once you understand that one, you will certainly have an easier time with the quadratic case, but the quadratic case is a little bit different. Okay, so let's jump in. So here's our first example. So we're going to be taking a look at this one, and then we'll kind of step through all of them. Now, as I'm doing the first example, I will do this one a little bit more formally, and then all the other examples, I will just simply be finding the delta for you, right? Okay, so every proof that you have for epsilon delta, so if you're putting it on an exam, test, quiz, so that you have your profs or TAs marking it for you, and then try to follow these two steps. Very often when you're doing these epsilon deltas, people just jump directly and then they just try to find the delta, period. Okay, and then that's all that they do. And most of the time they'll get frustrated because they'll lose marks because there's no formality in your proof. So you have to actually state, okay, so first, what are you doing? So you're finding a delta for a given epsilon. I know it's a nuisance to put that in there and it's annoying, but if you want the full proof, then you have to do this. So that's the first step that you would do. All right, so check. Okay, step number one. Now you can go ahead and proceed in trying to make these connections between f of x minus L and then x minus A. So we're basically just establishing a needed delta. All right, so let's do that. So I'm going to do the next item, which is this one right here. So now in your connection, what we are trying to do is when you're taking, this is just in general. So when you're taking this right here and you substitute it in, so you'll substitute your function, all right? So in our case, our function is x squared minus the limit turns out to be 1. So we have that. And then you're comparing it to this right here, which is your x minus a. So what do we mean by creating a connection? Well, the connection is made in such a way that you want this right here to be less than, well, I mean, it could be equal to, that's fine, but it could be less than or equal to, then some bound, where this bound is just simply a constant. So it's just a number that you can find. And that bound is just multiplying this x minus a. That's the connection that we're trying to do. So how do we relate these two things together? How do you go from here and all the way to something that looks like this? So in our case, what we're going to have, and you will notice that we're going to come up with something like this. This bound is actually going to be equal to 3, and I'll show you why. And then this right here, which is x minus negative 1, that's for our limit. That's what we will have. And our ultimate goal will be, once you make that connection, then you want this to be less than epsilon, right? So this less than epsilon. And then what do? Well, you simply divide both sides in this case, all right? So you would have divided it by a constant b, and this would have been divided by b. And you would have found your needed delta. So you would have been able to establish a delta. So in our case, we would have had something like this. Now this, I'm going to just simplify this with the negatives. So you would have had something of this nature. And then you would say that this is your delta. So why was this 3 for this example? Okay, so let's see that happening. Now, this is 3 because, so if you take this right there, and I'm going to steal this out, okay, and you can create a factor because it's just a quadratic, right? X squared minus 1. And so now for here, so I'm going to say that this is actually equal to, and you will notice that this is just a difference of squares. So it's going to be x minus 1 multiplied by x plus 1. And well, there you go. So here is your, so right here, that's what we wanted to make the connection with. Well, you have it right there. So now what you're trying to do is you're trying to find this bound. All right, well, R3. So now you might ask, why in the world did you make this 3? All right, so that's a very legitimate question. So why is this 3? So you know that for these quadratics, so if you have, so quadratics are actually defined everywhere, right? They're continuous, okay, so they're a very well-defined function. So we technically don't really need epsilon deltas, but since you're learning about them, we have to now understand what happens. We can't put a bound on this with a constant if x is unbounded. Because if x is unbounded, so if you take this and you have, right, so this is your x, and it doesn't have a bound, right, it can be anything, so it can go on to infinity, then you will notice that, well, this will go on to infinity because it's just x minus 1. So if this is going to be something really big, meaning x is going to be really big or really small, so either positive or negative, so depending if it goes all the way over here or over here, then you can't find a bound. So how do you do this? How do mathematicians overcome this problem with these particular limits? Well, what they do is they say, well, we can't just have it for any x. So we're going to bound the x, all right, around our limit. So what they do is this. So we are approaching -1, all right? And now I'm not going to go all the way, as big as I want, and I'm not going to go as small as I want. And therefore, what mathematicians will do, they will say, okay, so for this, so around this bound, so this is how you would write it. Okay, so we would have this, and we want to be making it less than something so that we can put a bound on x. So x is fixed. It's going to now be within some domain that's going to be a fixed domain. It's not going to be infinitely large. All right? And what mathematicians will do is they will choose this. This is completely arbitrary. You can choose this as any number you like. But for convenience, they typically will choose this as 1. And you will notice that your profs most likely will do that as well. So this is purely by convenience. Now, what does this statement mean? What it means is that around this value, so -1, all right, you are only choosing, so because I put less than, because we want to put a bound on it entirely, so this is going to be, I guess, 0. And this right here is going to be -2. So notice that is, +1 in this direction and -1 in this direction, and that 1 is coming from here. Now, if you set this to 2, then, this would have shifted over, and this would have been 1, and then this would have been -3. If you made it 3, and then again, it would shift over. So now you might say, well, why didn't you make it bigger, right? It's just purely for convenience. For the sake of the proof, we don't need to make it bigger. We will just say that we're interested in vicinity for the limit, okay? So we'll assume that it's somewhere within here. And it won't cause us any headaches. Sure, it can be beyond, but you'll see how we can take care of that, okay? So now, that's what you will do. And this will be a trick anytime you have something in front that you want to put a bound on, which is in front of this, the x minus your a. So if you want to put a bound on this and it's unbounded, right? If this was a constant already, then we're done. That was the linear case. But because it's quadratic now, we're not done, and we have to now put a bound on our x. So if I put a bound on this x, then what I can do is, so I'm going to steal this back here. Let's duplicate it, bring it back down. Okay, so, less than, all right, okay, or equal to. And I'm going to now use inequalities in here. So I'm going to say this is going to be x. So notice I'm taking the first term, I'm putting an absolute value. Okay, so that's why I have put here less than or equal to. And then instead of the negative, I'm going to put this as plus, because plus will be bigger. and of course, the absolute value of 1, which really is just 1. So we have now this right here. And you will do that anytime, okay, that you have kind of a polynomial in here. So you can just put bounds on it, and then you know that it's going to be less than or equal to this. So we're being conservative. We're trying to find the largest value possible on this right here. And now, because we have restricted, all right, this to be within here, so what we will write, we will simply state, okay, in here. So let your x, so be placed in such a way that this holds true. All right, so that this right here holds true, that we're just bounded within 1. Now, if that's the case, we want to be able to now find this. Can we find a numerical value if indeed x is just bounded by this 1 within here around the limit, plus minus, right? Yes, we can, right? So you can now pick any values you like in here to make this as large as possible. Well, the largest thing possible, just hint, you will pick the boundaries. So it's going to be one of the boundaries. So either 0 or it's going to be -2. So in here, it will be -2, all right? And now, because of the fact that we make it less than, so we have to now be careful, and we'll say, okay, so this is going to be less than. And that less than now comes out. So notice if you put negative into 2 into your x, okay, you put absolute values, it's going to be just 2. And this is going to be just 1. And then you have x plus 1. And that's how we found our 3, right? So this is equal to now 3, and then x plus 1, which is exactly what I was showing you right here. So now, because we want this to be less than epsilon, well, now you can take both sides divided by 3, and there you have it. So you have now established your delta. So your delta now is going to be epsilon over 3. And this is epsilon over 3 within that range, okay, around 1. So right here. Now, what happens if, because x is not necessarily just bounded within here, it could be bigger. So what happens, how do we take care of that? Like, how do we know that this might work? Well, so what we will do is we will just simply say, let our delta be equal to the minimum of what we have chosen. Okay, so either 1. So if it goes beyond, well, we'll just make it smaller. Or epsilon over 3. Okay, so if it's epsilon over 3, that's for this particular region. And then if it goes beyond, we can just say, that's fine. Let's just minimize our delta to 1. It's not going to be the ideal delta, then you can find a bigger delta if you wanted to. But remember, using a smaller delta will work if you know that a bigger one, okay, has satisfied your proof. So there you go. So that is our delta. So now, what's next? Well, so in order to finalize your proof, now you have to show, so this is your step number 2, you have to show this. So I'm going to copy this down. So now we're going to be showing that for what we have found, so here's our delta that we have found, that it actually works. Now, what do we mean by works? It means that if this is true, so in our case, so what we have, so if x minus -1 is true, okay, so if this is within delta, then what we want to be able to see is that f of x, which would have been x squared minus 1, is going to be less than epsilon, right? So that's what we want to be able to see. Now, we already know what this delta is, so that delta is chosen to be within here. So notice what happens, that here again, so you're going kind of in reverse. So this was equal to x, minus 1, and then x plus 1. You know that this is going to be less than, all right? Okay, so now here, so this right here, we know that this was 3, so this is from what we've established above. And this right here, All right, so that is just can be less than your delta, right? So delta within here, so you can now pick, okay, so out of the minimum, it's 3, and therefore the 3 and the 3 cancels, and this is nothing else, but simply you're just stuck with your epsilon. And that is it. So now you have shown, all right, okay, that your delta works, okay, for the statement. And that would have been completing your entire proof. So you would have to actually show this to your profs to complete this. So that's one example that you have in here. And now in order to practice this, now I'm not going to go through, you know, step 1, step 2. You can certainly do that. You've seen it now once, and you know you've seen it if you've watched my previous example, you know, you've seen it again. Now, you know, because then the video would have been really long. Okay, so I'm just going to now find the deltas for you. Right, so I'm going to just skip, you know, all of the steps. So what would we do in order to find our deltas? Because that's ultimately what you want. And so here again, if you notice that it's a quadratic, okay, so within here, so what we will have is the following. So we're going to have, so f of x, which is 2x squared minus x. So that's your f of x, minus your limit, which is going to be 6, right? Our ultimate goal within here is to find some bound, and that bound is going to be multiplying x minus 2, all right? So in this case, because that's what x is approaching. So we want to find this bound. And then once we find this bound, you're done, because then this is supposed to be less than epsilon. And then what you will have is that your delta is going to be within here equal to your epsilon over whatever bound that was, okay? So let's do that. Okay, so from right here, because you have, you know, a quadratic, so this is something, you know, that I would want to remind you of. This always will factor into, you know, x minus your a. Why? Well, if the limit actually exists, so notice, okay, if you substitute 2, right, because how did the 6 come about? Well, if you substitute the 2 in here, you're going to get your 6, right? So you know that this is a factor by the remainder theorem, meaning x equal to 2, okay, would make this polynomial equal to 0. Because if you substitute 2 into here, you're going to get 6 minus 6, which is 0. So this is always going to be a factor, meaning that x minus a is always a factor, which now makes your life easy, because you know one factor. You just now have to find the other factor that you have. All right, and now so for the other factor, so within here, so this right here, so this is 2x squared minus x minus 6. So this is going to be 2x, and I guess this is going to be plus 3. Now, that is just factoring quadratics. So I'm not going to go into factoring quadratics. You can certainly go back into that. I can put up a video all the way from high school, okay, if you want to. So I think it was like in grade 9 or 10. Okay, you can certainly take a peek at that. So you can convince yourself that this indeed is a factor. And now this we want to be able to put a bound on. And again, so how do we put a bound on this? Well, so you will take, so this is going to be just 2x, okay, so plus 3. So this is going to be less than that, right? So x minus 2. And now again, so we take, because, you know, x can be as large as we want, so what we will do is we're going to say, all right, let, you know, x be chosen in such a way that we have x minus 2 to be less than 1. Again, this 1 that you see is for convenience. You can choose 2, you can choose 3, right? But typically we will choose 1 just purely for convenience. And again, what it is saying is that we are now moving along. So here is your 2. So we are 1 away. So either in this way or this way. Okay, so like this. And now we want to find when this is the maximum. Well, it's going to be maximum at 3, right? So now I have to be careful because I'm not including, right? So this is, okay, so this is what I'm going to do right there. Okay, so now if I substitute that in here, so 2 times 3, 6, 9. So this is going to be just 9. X minus 2. There you go. You found your bound. All right, so that is your bound. So therefore delta is going to be equal to, now again, you still have to state minimum. So it's going to be minimum between the one that you've chosen, okay, or so whichever one is smaller, and your epsilon over 9. All right, that epsilon over 9 just simply comes from here, because you would have made this less than epsilon, dividing both sides by 9, and then you found it. So that's how you would find your delta for here. So notice that the process is pretty much the same as the previous one. So let's jump in and see another one. Now again, this is not a complete proof, this is just finding delta, and then you can follow the other steps. So here's another example. So let's take a peek at this one, and you'll see that these are going to be, now we can fly through these because they're consistently the same process. All right, so let's begin and try to find our delta. Okay, so here, what do I have? I have 1 minus x squared minus, so this is negative 1. All right, and I want to relate it back to, so again, I need some bound, so I need some constant. Okay, and then x minus 1. All right, so what's that constant? So what's the step process? Factor. I have to factor this out. All right. So now I'm going to just massage this out because just the way that it's set up. So what I'm going to do, okay. Now when you're taking absolute value, so that negative is going to be gone. So this is going to be the same thing as writing just x squared plus x minus 2. And now factoring it, so I know that one factor is x minus 1. Now I have to find the other factor. So that other factor, so not bad. So this is going to be x. This is just going back again to factoring. So it's going to be, I guess, plus 2. Okay, so you can just double check for yourself. So now I need to bound this. So how do I bound it? Well, we let x, okay, to be, in R such that, okay, so x minus 1 is going to be, and again, I'm going to just put 1 in here. So for convenience, that's what I will do. So now that I have this, okay, so now what am I doing? Trying to maximize that x plus 2. So this, to maximize it, that's what I'm trying to do. So around 1, so that would have been 2 and 0. Okay, so within here, this is going to be less than, and well, that 2 is going to be, this is 4, x minus 1, and now there you go. You found your delta. So delta again is going to be the minimum, so of 1, and so in this case, epsilon over 4. And that's what you would have. All right, so that would have been it. So very quickly, I hope that you can see that there's now a pattern that evolves. So here is, another example, because sometimes, you might take a look and you're not sure what to do when you have maybe a quadratic that's not in the standard form. So here's, an example of a limit when it's not. This is the vertex form. So if you remember that parabolas, so you have a vertex and then which way do they open up, open down, you can do quite a lot. This is again going back to high school and how much you remember about quadratics. So if you're given something like this, don't fret. You will do exactly the same thing, and in fact, this right here, you can certainly, this is just x squared. So there you have it. All right, just some quick math. This negative is gone because of the absolute value, so we're just dealing with this right here. And again, we know that, so this is going to be 3, so it's x minus 3, so that's one factor, and then now we just need the other factor. So it looks like it's going to be x plus 7. All right. So there you have it. And now again, we want to put a bound on this. All right, so how do we put a bound on this? Well, we restrict where the x is. So again, we're going to have to be restricting this, to be, again, I'm always picking 1. Mathematicians will always do that just for convenience. You can pick, 2, 3. You can put 0.5 if you wanted to, which would restrict it further. But, so 1 is very convenient. So now again, so within here, so you are, what this is doing is, so around 3, you're saying you're bounding it by 1. So it's going to be 4 and 2. And now you want to find, the largest value for this. Well, that's when x is equal to 4. Okay, so 4 within here, because they're all positive numbers. So that means that this is going to be bounded by 11. And then you have your x minus 3. And this is your constant. And this will mean that it's going to be epsilon over 11. All right. And again, you can write delta is going to be equal to minimum between 1 epsilon over 11. So I hope that you now recognize that, this pattern just keeps continuing, right? So as long as you have, now these are all quadratics, right? So the same thing worked for linear case, and then you can probably guess, it's going to be working for the cubic case and so on in terms of polynomials. Now, hopefully you're not going to get anything bigger than a quadratic or cubic, because then your factoring is going to be a little annoying. So here is now the generalized case. So I just want to show you, as the thumbnail points out in the video. So here's the general case. So you have a quadratic, right? It's in standard form right there. We're going to assume that this a in front, this capital A, is not 0, because then it wouldn't be quadratic. It would be linear. And if it's linear, we've done that before in the previous video. So, if this limit, does it really equal to this, right? This is what we want to be able to find out. And then again, if you were doing it by epsilon delta, so it's equal to that, right? It's a quadratic. It's a well-behaved function, so there's nothing to worry about. So this is definitely true, but we still have to prove it. So in order to find our delta now, well, so this is going to be neat. And notice what will happen, right? And now we want to make our relationship with, okay, so we want this, again, we want some constant, okay, so within here, I'll put a little c instead of using the b, which I used before, because we have a b on the left-hand side. So x minus a, that's what we want. That's what we want to find. What in the world is this c? That's what we're looking for. So now, if you massage this out, what will we notice? We'll notice this, a, and this term c minus c is gone. So there's nothing there left. And now, this is exactly what we want. So notice within here, because we want a relationship with x minus a, well, we have x minus a here. And this is just a difference of squares, right? So we have a, x plus a, x minus a, that's what this is equal to, plus b, x minus a. So beautiful. So we can take this out, right? We can factor this out. So if you factor this out, you're going to get to that. So all of these are equal. So we haven't even done any inequalities yet. So that's what we wanted, and now we want to put a bound on this, right? So that's what we were doing all the time. So how do we put a bound on this? Well, so you can say that this is less than or equal to. Now, so here it's going to be a little bit, annoying, but that's fine. So again, I am doing that. So now I'm putting less than or equal to, and I want to maximize. So again, I want to put a bound, complete bound on this. So I don't know what this capital A is, right? It could be positive or negative, so that's why I'm putting it in brackets. I don't know, okay, what this and this will be, so I'm putting it all in brackets. So I'm just dealing with positive numbers. This is just an inequality to make sure that we are bigger or equal to this. And now, again, you have the problem with x. So you have to do x minus a. And then again, so this is your little math trick. Okay, so let's just bound x. Okay, let's not make it infinite. So what this means is that here it's a little bit trickier than the other ones, because in the other ones we actually had values. Now we don't have a value. So we're around a. Now we have no idea if a is positive or negative. So, but we do know this is going to be a plus 1, and this is going to be a minus 1, right? And now, again, we don't know, okay, so, which one is going to maximize? Is it going to be this one or this one? But what we do know, 100%, is that if you take, so for instance, if you take a minus 1, okay, so this definitely is less than or equal to a plus 1, right? And the same thing is true for a plus 1. So both of these, okay, hold true. So that's what we're going to pick. We're going to now take this right here to substitute for x. And when we substitute that, because we know that these are going to be bigger than whatever we had, okay, coming out of here. So if you now substitute that in, so this is just now massaging it out. So let me just substitute it, okay, and then collect my like terms, etc., and then you'll see what the answer is. And now all you have to do is just say x minus a, this divided by this junk. Okay, so it's going to be divided by that, and you have your answer. All right, now you can set your delta. So your delta is going to be the minimum of 1 and epsilon all over 2a plus 1 multiplied by this a plus this b. That's it. And this will generalize for all your quadratics. Now, by the way, and I will add this so that you can play around with it if you want on decimals so that you can see. So on the right hand side you have decimals. Okay, you have an epsilon. Notice that the delta on the left, kind of in the middle, as you see there, is minimum between 1 and epsilon 3. So if you go back to that original one, this is what you had, and then for any epsilon, notice that it just changes it up. Okay, so let me make it bigger now so that you can see it. Okay, so this is exactly what we wanted to see, right? So you have within, you are stuck within a delta, and now if you're within that delta, does it guarantee that you are an epsilon away from the limit? And indeed, that is the case. You can play around with this back and forth to make it visual. And also, what I would put in, okay, notice that you can now change your A, your B, your C, whatever it is that you like, so that you can play around with this, and then it will update it for you so that you can visualize it. If you're a teacher, you can certainly use that. All right. Okay, thanks for watching. I hope that you found this useful. We'll see you in the next Epsilon Deltas. Bye, everybody.